Okay, so this is the second set of atomic structure questions. They are all multiple choice. They're all past paper from AQA A-level chemistry papers. My advice would be to have a look at the question, pause it, try the question, and then follow the video through to double check and see how you've done. Okay, first question coming up. So quite a lot of information to take on here. We've got the idea that helium 2+ particles are being fired at the thin sheet of gold, but only about 1 in 8,000 of the particles are detected at point Q. Now, most will pass straight through. The question really is, why is that the case? Now, as you go through each of the answers, A, B, C and D, there's one that really does stand out. And that's the idea that if very few are reflecting back, it means there's very little to reflect back from. So, correct answer that we're aiming for here is that gold atoms have a small positive nucleus. The vast majority of the helium ions will pass directly through the thin sheet of gold. They won't be deflected at all, but that tiny number of them will be deflected back when they hit the small positive nucleus. Okay, on this question we're dealing with isotopes. We've got two isotopes of bromine, 79 and 81. And we want to know what statement below is correct. So let's take a look at the ones that we know are not the case. Well, when you consider ionization energy, the change in ionization energy is dependent on the attraction to the nucleus and the shielding by inner electrons. That's no different in the two isotopes, only number of neutrons is different. Atomic radius, similarly, is impacted on by the attraction to the nucleus of the outer electrons and the shielding, and there's no change there. And reactivity is about bromine gaining electrons, and there's absolutely no difference in terms of the attraction, so they are also the same. So that leaves us with the correct answer. And when you add up 3 carbons, 7 hydrogens, and a bromine 79, it gives you an MR of 122. When you take 3 carbons, 7 hydrogens, and a bromine 81, it will give you a value of 124. And so you do get those 2 molecular ion peaks. Okay, a relatively straightforward electron configuration question. So we want to know what the electron configuration is of copper 2+ ions. Now, this is copper itself. It's one of the 2 anomalies, copper and chromium, whereby one of the 4s electrons actually shifts into the 3d, giving us a half-filled 4s and a full 3d. But that's not what the question is. The question wants to know about a copper 2 ion. So we're going to lose 2 electrons. You have to remove 4s before you remove 3d. So it's absolutely vital that you remember that fact. And when you do, you can see that we have lost our 4s and our 3d10 has gone down to 3d9. Okay, so here we want to find out which requires the largest amount of energy. Let's start by writing out the electron configuration of what we are starting with. Or certainly, helium 1s2, 2s2 is its electron configuration. Lithium 1s2, 2s1, magnesium 1s2, 2s2, 2p6, 3s2, and nitrogen 1s2, 2s2, 2p3. Now, bear in mind that we are in some cases looking at first ionization enthalpy and in some second ionization enthalpy. So the next thing to consider is where the electron is being lost from in this particular reaction. And we can see in helium that for second ionization energy, we've already lost the 2s2, so this time we're losing the 2s1. Lithium, we're losing the 2s1. Magnesium, we're losing the 3s1, and nitrogen we're losing 2p3. Now I am immediately going to disregard C and D because they are higher energy sublevels and actually in the case of magnesium a higher principal energy level. So you would expect those values to be lower. When we take a look in the case of helium and lithium, the big difference that we have is that lithium, you are subjected to shielding by the inner electrons, but in helium, there is no shielding. So that takes us to the correct answer of A. There's a huge amount of information here and very little of it is actually needed. We want to know essentially what the correct electron arrangement is for a copper +1 ion this time. We looked at +2 earlier. Now once again I've put in the copper atom electron configuration 4s1 3d10, and once again it's absolutely vital that you remember that the one electron that's been lost here is being lost from 4s. We fill 4s first, but we empty 4s first as well. So the correct answer is D. Okay, so we're now considering the strength of reducing agents. Now let's try and break this down to some of the chemistry basics so that we can identify very clearly and very effectively which one is the strongest reducing agent. The strongest reducing agent is the one that's most easily oxidized. Oxidation is loss of electrons. A reducing agent will donate electrons, and it's therefore about considering which of these will most easily lose or donate their outer electron. So which one will do that most easily? And if you take a look, D, its outer electron, is in the 4th principal energy level. It's much further away, it's less attracted to the nucleus, and it's subject to more shielding. For those reasons, that's why D is the strongest reducing agent. So in this question, we want to know which does not have a pair of S electrons in its highest filled electron energy sublevel. So a couple of things to consider here. One, we are looking specifically for the outermost electrons being a pair of S electrons. Secondly, this is a negative answer question. We want to know the one that does not have. So always read the questions carefully to look out for that. Because you can see that H- would be 1s2. It therefore does have a pair of S electrons in the highest filled electron energy sublevel, so it's not the right answer. Magnesium, we can see, ends in 3s2. Phosphorus, well, phosphorus as an atom is 1s2, 2s2, 2p6, 3s2, 3p3, but we're not asked about the phosphorus atom, so we need to get rid of the 3p3, which does mean that it's 3s2. And D, finally, we've got argon, which ends in 3p6 and is therefore the correct answer because it doesn't have a pair of S electrons in its highest filled electron energy sublevel. Now, there's a similar theme here. You can work it out. You can draw out or write out the electron configurations, but you can also use the periodic table to help you on this. And I've done that here. I've found those 4 elements. I've color-coded and highlighted them on there. And it's important that you remember, as a really basic detail, the S block, which is on the left-hand side, we can see lithium and beryllium at the top of it, that's 2 wide. And the S sublevel holds 2 electrons. So anything that's in group 2 has a full S sublevel as its outermost sublevel. The D block, going from scandium across to zinc, is 10 wide, and a D sublevel holds 10 electrons. So anything that's in the 10th, so zinc, cadmium and mercury, will end in D10 and therefore have a full sublevel. The P block on the right hand side, to have a full P block you really need to be a noble gas, and we can see here germanium is second in of 6 in the P block. We know that that's therefore going to end in a P2. That's an incomplete sublevel, and that takes us to the correct answer.